Okay, so now we're going to compute the 4-point function, but we're going to compute the connected correlator, and we're going to amputate the external legs. So this is a P1, P2, P3, and P4. And we're not going to do the computation, but I'm going to write down the diagrams that participate just to remind you, because we've already done this calculation, and I just want to remind you of some of the details, and you can go back and look in your notes for some of the formulas. I'm just going to quote. They're formulas that we obtained previously. So there was one tree diagram. There were 3 one-loop diagrams. And this is what they looked like. And now we get one extra diagram because we're using the normalized perturbation theory. And the extra diagram comes from the counter term for the coupling. So that's the only change, just one extra diagram. And let's just write down what is the answer. So we'll have minus I 4 factorial GP. So I'm sure you know how to get that. That diagram is particularly simple, no symmetry factors or anything like that. So the combinatorics is trivial. And then from these 4 diagrams, we actually calculated them, okay? And the answer was written in terms of a function, which we called V. And if you remember, to calculate these diagrams, we had to do a non-trivial loop integral. And this is actually the integral that we used to illustrate in general how we compute Feynman diagrams. So you have done this in detail. And let me just remind you of what this function V of P squared is. Well, there's a 288. Where does this 288 come from? It's 4 factorial times 4 factorial from the 2 vertices divided by 2 for the equivalent lines. Then we also had a GP squared, which made sense for the vertices. And then we had a 4 pi squared. This came from doing the integral because we evaluated this in dimensional regularization. There was an integral over the Feynman parameters. So it was dx from 0 to 1. And then we had the divergence, the 2 over epsilon. So we should be setting epsilon to 0. So that's the divergent term. We had minus log x times 1 minus x and a p squared. We've got minus the Euler-Mascheroni constant plus log of 4 pi. And then there were terms of order epsilon that we dropped because we're going to be taking epsilon to 0. Good. So that was the result from the 3 loop diagrams. And then for the last counter term diagram, it's just minus I 4 factorial. So it looks just like the interaction vertex, except that we now need the counter term. And so usually we would just write this as delta G. I'm going to put a 1 here to stress that we're working to order H bar at 1 loop. That's all we'll get. And I'll keep the H bar there, okay? So I've put in all of the H bars. In fact, you know, you usually would not put the H bars. So let me not put them in black. I'm doing this just because for us to understand the calculation. So we usually always set H bar to 1. But let me just keep the H bars here so that we really understand what we're doing, because it's always good to have them there to match them. Okay, then we're going to use the matching condition, okay? So let's just discuss what that would give us. So use the matching condition. And let's just remind ourselves what that matching condition said. So where was it? It was over here. So we should set the connected amputated piece of the 4-point function equal to minus 24IGP at these sums of the squares of the momenta is equal to minus m squared. So what does that mean? Well, our 4-point connected Green's function is equal to minus 4 factorial GP plus a whole lot of stuff at order H bar. So the matching condition is telling us to set all of the additional stuff to 0 at p squared, p1 plus p2 squared equals p1 plus p3 squared equals p1 plus p4 squared equals to minus m squared. So we set all of those h bar terms to 0. So the matching condition says naught is equal to, there'll be 3, I've just added up the 3 b's, minus n squared minus 4 factorial I delta G1 equal to 0. Okay, and I've dropped the h bar because everything was order h bar in this equation, so I can do that. So if we solve for delta G1, well, that's an easy thing to do. This tells us that delta G1 is equal to 3 times by b of minus m squared divided by 4 factorial I. Okay, good. So now let's plug in the value of this counter term. So can you see, I mean, maybe just to labor the point a little, the matching condition has determined our counter term, as we said that it must. Let's now plug our counter term into our expression for the correlator that we're looking at. And what is it equal to? We've got P1, P2, P3, P4. What is this equal to? Well, the first term is minus 4 factorial times by I times by the physical coupling. And then we have got plus V of P1 plus P2 squared plus V of P1 plus P3 squared plus the V of P1 plus P4 squared. Then plugging in the value for the counter term, we have just minus 3B of minus m squared. Okay, and it's not fair if I have all of the fun in this course, so I will leave you to actually work out what that is equal to, and I'll just write down the answer. So this is minus I 4 factorial t physical, and then the second term is minus, we've got 288I g physical squared divided by 4I squared. And then we have the log of minus P1 plus P2 squared over m squared plus the log of P1 plus P3 squared, should be a minus here, over m squared plus the log of minus P1 plus P4 squared over m squared. Good. And the second term is, of course, of order h bar. So let's keep that in place. This is going to pay a big time. Let me just write this as A plus B and then multiplied by the h bar. Good. Okay, so what do we want to do? Well, now we want to plug this into Kalam-Sarmanzik. So what would Kalam-Sarmanzik say? Well, Kalam-Sarmanzik says m d by dm plus beta times by the physical coupling plus 4 gamma on G4 is equal to 0. First thing that we can do is that this term vanishes because we said gamma is equal to 0. Now, I want to stress something about the beta function and the gamma function. If we were to study the beta function, well, because we're working in perturbation theory, in loops, there would be an expansion of powers of h bar. And in fact, the beta function starts off with h bar beta 1 plus h bar squared beta 2 plus and so on. But I just want to stress that the beta function starts off with an h bar, and so does the anomalous dimension. So the fact that the theory, that parameters in the theory run with scale is a consequence of quantum corrections. Okay. So now let's see what Kalam-Sarmanzik would tell us. So we'll have m d by dm, and the thing that I'm specifically interested in doing is getting the h bars right. So we'll have h bar, we will have beta 1, So this calculation is only going to fix the one loop contribution to the beta function, as you would expect. The derivative of the physical coupling, plus 4 gamma, well, we can write plus naught if you like. And then for G4, we can write A plus B, and there will be an H bar, okay? And this should be equal to 0. Okay, so let's look at the various terms. So of order H bar to the naught, we've got M d by dm times by A plus. Now let's look at the terms of order H bar. So for the H bar terms, we will have beta 1 dA dGP plus, and you'll have M d by dn acting on B. And this we'll have plus, let's say, order H bar squared, which we have not reliably calculated, so we can't consider those terms, and that will be equal to 0, okay? Now, what you see is this M is the scale at the matching condition, but A, the first term, well, that's kind of the classical piece. That's the piece that is fixed to measured values, so that doesn't depend on the normalization conditions at all. You can see what is A equal to? Well, A is just minus 4 factorial GP. So this first term, M d by dm on A, vanishes. We don't have to worry about that. M d by dm acting on minus I 4 factorial GP is 0, okay? Then we can take beta 1 dA dGP. Well, if we differentiate A with respect to GP, we're just going to get minus I times 4 factorial. So we will get, so now we're looking at, let's say, this piece over here. What does this give? Well, we've got beta 1, and the derivative of A with respect to GP is just minus I 4 factorial. So we'll have minus I 4 factorial. Great. And then we'll have plus M d by dm acting on the B. So let's see what M d by dm acting on the B is. So we have to take M d by dm of this quantity over here. So what is B? B is this thing sitting over here, okay? So the first thing that I'm going to do is I'm going to lift this constant from up front, okay? So we've got, what is it? It's 288. It is I GP squared, and this is over 4 pi squared, okay? Over 4 pi squared. Great. 288I GP squared over 4 pi squared. Good. And now we've got the M d by dm. Well, if we take the M d by dm, I'm going to get the same contribution from all three terms here. I can write log of minus P1 plus P2 squared over M squared as the log of minus P1 plus P2 squared minus the log of M squared. So I've basically got minus 3 times the log of M squared, and M d by dm acting on the log of M squared is just 2. So I'll get a minus 6. The minus sign cancels with the overall minus of the square bracket, so I'll just get a 6. Okay, so this is just elementary calculus. I just took a derivative, okay, and this is the answer for the derivative. Okay, so let's go back to black in Winehouse. So beta 1 is equal to, it'll be 6 times 288. We'll have a GP squared. We will have 4 pi squared. We will have 4 factorial. And remember that 288 was 4 factorial times 4 factorial divided by 2 for the 2 equivalent lines. So then it's pretty easy to do that division. And we just get 72 GP squared over 4 squared. Great. So this is the beta function to one loop. So to one loop, we have learned that the anomalous dimension vanishes and the beta function is equal to 72 GP squared over 4 pi squared. And this is the anomalous dimension and the beta function to one loop. Okay, what we want to know now that we've got these answers, we'd really like to understand what is the physical interpretation of these quantities, the gamma and the beta. And that's what we're going to develop next.